it actually is problematic, I will have to do that, yeah, as if it's not right. Reviewing, on Monday and Tuesday, we talked about Faraday's Law of Induction, electric generators, inductors, transformers, and AC circuits. Today, we're going to talk about Maxwell's equations and electromagnetic waves. In today's lecture, there will be no calculations, no equations you have to know. There are plenty of equations. You just don't have to know the equations from today's lecture. And unless you're David. I wish I could read this better.
I was hopeful.
Yeah, good hope. It's always safe to hope. So, what's going to be on the exam next week? Next week, it's going to be covering chapters 22 to 24. Small section, but really not easy stuff. Right? We spent a really large amount of time on these two chapters, 22 and 23. And today's material is the last stuff to be on the test. Everything from today, it's conceptual. You're not going to solve problems with it, but in the first questions where it's asking you about ideas and those kind of things, that's where things from today's lecture could come from. We are going to cover transient circuits because I was supposed to cover those like in class on Monday and didn't get to them. And so they're off to the side now. Hey, Max. So let's get into Maxwell's equations and electromagnetic waves. So starting off, let's connect up with whoop clap, everybody's favorite.
What if I felt this way? That would be depressing.
I don't even know what I'm Me too, who clap? Are the windows showing apart because of the
I don't know. Oh, no, I do know, actually. They're closed because I was doing something with light in my previous class, and we needed them off for that. Because, believe it or not, they're now ahead of you. Okay. So moving on, let's get to our first question. Oh, actually, it's not our first question until after this. James Clerk Maxwell. Okay, so unimportant, yet it helps you put a little handle to hold ideas together. James Clerk Maxwell's family name was Clerk, not Maxwell. But his father inherited some property, and with it, the name Maxwell. And so Maxwell was appended to the name. So if not for his father's inheritance, he would have been James Clerk. So sometimes you see the name James Clerk Maxwell, and people think Clerk must be a middle name. Not. Okay, so in 1855, he did his original work, in which he took an enormous number of equations to describe electricity and magnetism, and he condensed them down to just 20 differential equations. Right? That's what David's been studying, right? Does it have a question? Dave.
I don't know.
Let me back that up so you can't answer the question. Okay, so he condensed it down to 20 equations, which he wrote and presented in 1855, but it wasn't published until 1861, so the 2 days are both important. In 1861 or 1862, he actually calculated that these equations he had come up with, that he had condensed, right? He was doing mathematical manipulations. They predicted that you could make a wave out of electric and magnetic fields, and that the speed of this wave was the same as the known speed of light at that day. And so he said, aha, it has the same speed. It must be the same thing. Light must be an electromagnetic wave. That's kind of like saying, I'm running the same speed as that car, hence I must be a car. That's the logic he used, but it turns out he was correct nonetheless. It's good when your accidents are correct. These days, we believe that, for instance, gravity travels at the speed of light, but nobody says gravity is an electromagnetic wave. It's a completely different thing. So he made a logical jump that wasn't very good, but it was correct. A few years later, he was able to simplify those 20 differential equations down into just 4. So he came up with just 4 ultimately differential equations that describes all of electricity and magnetism. Now, I was talking to Dr. Osborne about this last week. He said, well, no, somebody else, actually, did a lot of that work. I was looking it up, and of course I was looking at Wikipedia, which we know is not the end-all of knowledge. And Wikipedia actually contradicts itself. Wikipedia says that he brought it down to these 4 equations, and then Heaviside worked on them and brought it down to 4 equations, Oliver Heaviside. I'm not sure, but they're still called Maxwell's equations, just 4 equations that describe everything in electricity and magnetism. Now, it sounds like that might simplify things because it's only 4 equations. But those 4 equations, you see David shaking his head, no, he doesn't really like them.
I know them.
You know most of them. David's like, what? So, we're going to look at those equations. First, there's Gauss's law.
Oh, I do know these.
First, there's Gauss's law. What we learned in this class for Gauss's law was very simple. We learned that the spacing between electric field lines is proportional to the strength of the electric field, and that electric field lines come into or go out of charges. And so as a result of that, the electric field lines are closer when you're close to a charge, farther apart when they're farther away from a charge, but it's the same number of electric field lines. And so this law says, basically, if you calculate how much electric field lines come out of the surface, you know how much charge is enclosed. So that's the first law. The second one is Gauss's law for magnetism, which is exactly the same law except for dealing with magnetic charge instead of electric charge. But the problem is magnetic charge does not come alone. We don't have magnetic monopoles. They're not known to exist. Theoretically, they could, but they're not known to. And as such, the magnetic charge enclosed is always 0. If you always have every positive has an equal negative, or in terms of magnetic charge, every north has an equal south, then the total is always 0. And so that Gauss's law for magnetism, we haven't even talked about it one bit because it's really not useful to us for calculational purposes. It will be useful to David next Tuesday when he derives when you take all 4 of them and use them to derive the wave equation for light. The next 2, Faraday's Law of Induction. Faraday's Law of Induction, well, we just covered that this week. A changing magnetic flux produces a voltage. That's what we saw. Putting it in its more general form, a changing magnetic flux produces an electric field. And then the final one, the Ampere-Maxwell law. Now, we've learned Ampere's law. Remember the circulation, we add up the magnetic field going around a loop and, well, multiply by the length of that loop. And it's equal to mu naught times the current going through the loop. But James Clerk Maxwell noticed a flaw in that law. So let's look at that flaw. He said, okay, let's suppose I have a capacitor. See the 2 parallel plates? And I have current flowing to the capacitor and current flowing out. But there's no current between the plates. Why is there no current between the plates?
Because there's no connection.
Because there's no connection. No current between the plates because there's no connection. How can you have current flowing to one plate and flowing away from the other plate and have no current in between?
Induction.
The capacitor stores energy in the form of an electric field or a charge separation. So we have charge accumulating on one side and leaving the other side. So the net charge is staying 0, but one side is building up a bigger positive charge, one side is building up a bigger negative charge. So what Clerk Maxwell said was, well, okay, this law said that if I take a circle going around this wire, so here's the circle going around this wire, and I add up the magnetic field parallel to that circle times the circumference of that circle, that will tell me how much current is going through. And sure enough, you find that the current times mu 0 is equal to the magnetic field times the circumference 2 pi r. But they said, what if I make a surface that goes like this? How much magnetic field is going through the red, or not magnetic field, how much current is puncturing through that red line I drew? How much charge per second is going through that red line that's going across it from the left side to the right side? That would be none. And the law didn't specify how you determine how much current is going through the loop. And so he said there's a problem with the law. What's happening in that loop is you're having a changing magnetic or electric field. And so he said a changing electric field must also produce a magnetic field, not just a current. And so he modified Ampere's law. He said, okay, what is the relationship between the changing electric field and the current coming to the capacitor? So current is delta Q over delta T. And we learned Q is equal to CV. So he just substitutes that in. And then we have the physical capacitance for a parallel plate capacitor. If it's air in the middle, we don't have to put the kappa, where L is the separation here. And V, if you have parallel plate capacitor, V is just E times D, right? Remember the equation on the equation sheet, delta V BA equals minus E dot delta X or something like that. If you have parallel plate capacitor, that electric field is just going to be the voltage, or the voltage is just the electric field times the distance. And so he substitutes that in. And then, of course, you can cancel the L's. So let's cancel those bad boys. This is a constant, so that came out front. And you have epsilon 0 times the change in electric field times area, which for this geometry, that is the change in electric flux. And so in the end, what he has is an equation that says there is an effective current, which he called the displacement current, when you have a change in electric flux given by this equation. And so he modified Ampere's law to say that the circulation is equal to mu watt times the actual current plus this displacement current. Now, like I said, you don't have to memorize these equations. You're not going to actually even use them. But it's important to know what's going on, why we have this equivalence between the changing electric field and the current, and thus a changing electric field creates a magnetic field. So that's the importance of this, is seeing that there is actually a connection. As David said, you shouldn't trust what I say. You should be able to look at those equations and analyze through and be convinced, yeah, that's a logical sequence of steps. So diversion, they're differential equations. There's no other way to show them in reality. These are Maxwell's equations. You have the differential form or the integral form. David has primarily been working with the integral form, except for when we did the calculation with that one. So this is the same four laws written in two different forms. And you have in this one here, notice it's del cross B. That means something completely different. So let me just bring to you what the important things for you to know about these are in terms of electromagnetic waves. The next to last one listed here is Maxwell-Faraday equation. Says that a changing magnetic flux will produce an electric field. Right? That's what you learned from Faraday's law. The last one, the Ampere's law with Maxwell's correction, says that a changing electric field creates a magnetic field. So changing magnetic field creates an electric field, changing electric field creates a magnetic field. Certain symbiosis between those, right? Question.
So didn't we know like the Maxwell Ampere equation? Like we need to understand why it's there and how to use it and stuff like that, but we're not going to use it.
That's correct.
Do we need all of these?
No, you don't need these. I mean, these are just the same equations again written out in another form. So yeah, no, you don't have calculus, right?
Change in magnetic flux will produce light.
Change in magnetic flux will produce an electric field. And change in electric flux will produce a magnetic field. Right, that's a really important outcome. And so it's from that relationship that James Clerk Maxwell was able to create what we call an equation that shows an electromagnetic wave can exist and that it has a speed of light that is, it has a speed that's equal to the speed of light. And so based on that, he said, we must have light waves. So you see these are popular with the nerd set. I have one that's way too small for me in my office. God said, and you see the left-hand one is the differential form, the right-hand one is the integral form. But those are Maxwell's 4 equations. And then there was light. Because those equations combined predict the light exists. Now, I'm going to have a little bit of my theological belief here. I believe that God created the laws of nature. And so I very much believe that these equations are summing up how we understand his creation. And we have light because of that. So fundamentally, I take this as true. Most people just, it's a joke, but that's how I believe. So what did James Clerk Maxwell do that was amazing? He decreased the number of equations incredibly. He actually came up with electromagnetic wave back when he still had 20 equations. But he condensed it down, so we just have 4, and they describe all of electricity and magnetism. If you include Lorenz's equation, which he actually did in his work, they also do relativity. It's all of electromagnetism, including relativistic electromagnetism, is basically summed up in these plus Lorenz's law. So it seems almost silly simple compared to all the difficulty we've been going through, but if you go through and work through these equations, you find that it's kind of tough, which you probably can accept that, right? And I didn't see people saying, oh yeah, this stuff is a cakewalk yesterday. All right, so now you can answer the question, Aaliyah.
Voting is closed.
Okay, now you can answer, David.
I think it's 84.
It won't take my correct answer.
It won't allow you to modify it?
Hey guys, I'm the one person.
Nope, you're not the only one. Somebody else after the lecture answered that.
Oh.
All right, we got 6 answers.
You know what?
Yay, we have 8 answers now. How many do we have here? 2, 4, 6, 8. We have 9 here. All but 1 is answered. Okay, so we had, nobody said 1, nobody said 2.
Hey, can you make that one with my vote?
Okay, Aaliyah wants to move her vote to here because she answered before we had any information.
That's what I heard first.
Okay, so these people were correct. He brought it down to 4 equations. That's the point of what I've been saying for the last 15 minutes. 4 equations describe all of electricity and magnetism with the most important outcome for us, a change in magnetic flux produces an electric field. A change in electric flux produces a magnetic field, and thus it predicts an electromagnetic wave. So now we're going to look at exactly how electromagnetic waves would be created. So if you have an electron and it's stationary, does it make an electric field? Yes. Charge makes an electric field. If the electron is stationary, does it make a magnetic field? No. You have to have a moving charge to make a magnetic field. So this stationary charge doesn't do it. But if I have this electron now, it's oscillating, then I'm going to have electric field because of the charge. and I'm going to have magnetic field because of the motion. So here's a picture to illustrate a dipole oscillating. What that's saying is I have positive charge and negative charge, and they're going like this. So when the positive is on top and the negative is down, that's going to make an electric field that goes out positive into negative, a downward point electric field. When they switch, it'll be an upward point electric field. So the electric field is going to oscillate as they move up and down. But if I have the positive charge moving up, then I have an upward current, and it's going to make a magnetic field that goes around it. If the positive charge is coming down, then it's going to make a magnetic field going the opposite direction. Notice the directions of the magnetic field versus the electric field. The electric field was oscillating that direction, and the magnetic field was oscillating between clockwise or counterclockwise. So in this picture, of course, it's a flat picture. So if it's going the way of the lower arrow, that's going in on the right and coming out on the left. If it's going the way of the upper arrow, it's going out on the right and in on the left. So in this picture, what color is represented by electric field?
Wait, what color is what?
What color is represented by electric field?
Isn't that the green line?
Yes. Green is electric field. And what color is represented by magnetic field then? That color, whatever it is.
Let's go with purple.
Not purple.
That's a good call, David. We're going with you. We'll talk about color blindness soon.
Oh, we don't need to. I'm not colorblind.
There's a good chance. Okay, we only have 3 guys total here, so there maybe isn't such a good chance. But men are much more prone to color blindness than women. It's a genetic linked trait. So the magnetic field directions are perpendicular to the electric field directions. And then there's one other important thing. The direction that the wave propagates is perpendicular to the electric field and the magnetic field. So electric field perpendicular, magnetic field perpendicular to the velocity. Right-hand rule type situation. And so you can look at this and you can figure out how the right-hand rule is going to work just by taking, let's say, for instance, this right here. I have my fingers like this. If the velocity is going that direction, the magnetic field, magnetic field like this. If I make my thumb the electric field and my index finger the velocity, and my middle finger the magnetic field, easiest to see if I go back to the first picture though, which I probably have repeated on the next slide. Just forgot where I had it repeated. This picture right here shows you how the right-hand rule is going to work for the directions for an electromagnetic wave.
How do they work again? Point towards where?
So we have 2 relationships here, one between the electric field and the magnetic field and one that shows direction. So we can combine those 2 into one equation that says it's got to be, you can't have division here, so we have to multiply by B max. And so I'll have believe that's right. If I take my hand, I put my index finger in the direction of B, and then bend my fingers to the direction of C, my thumb points to the direction of E.
Okay, so we point with our index finger towards E,
No more.
middle finger towards B, and thumb goes in the proper direction.
Wait, I thought I was pointing my thumb towards the B. Sorry, this finger.
Okay, so I made this on the fly, so we have to make sure I did it right. Index finger points in the direction of the first elements. That's B. So my index finger is pointing, this is supposed to be out of the board here. And then I need to orient my hand so my middle finger can point in the direction of C, and then my thumb points in the direction of the answer, E.
Okay. So B, then C, you get E.
So B, C, E is like that.
Wait, is that how cross products work? Do you point your index finger towards the first thing and
Yes.
then your middle finger towards the second thing?
Yes.
Genius.
Literally didn't get that until just now.
Better to get it now than later, right? Especially because we have a test with cross products coming up in 6 days.
In how many?
So glad that just worked.
Nice. Helps all of us.
All right, so this is how we have a real broadcasting antenna, one type of broadcasting antenna. You have a voltage source that's oscillating positive and negative, and the positive, well, one side is connected to one half of the antenna, the other side is connected to the other half of the antenna. And so as the voltage source changes between positive and negative, we're creating charge motion just like what we visualized in this picture. So we have current going up when we just change to the top one being positive, the bottom one being negative. And then they alternate when we change the direction on our sine wave. And so you have the current going up and down. It's creating the electric field when you have the positive charge on top and the negative charge on the bottom, or vice versa, creating magnetic fields that are going around in circles around us. Now, keep in mind, the direction of propagation has to be perpendicular to the electric field and to the magnetic field. So if these antennae went on forever, if they were infinite in length, then I would have a symmetry that would say everywhere the electric field is vertical only, and everywhere the magnetic field is horizontal only. And so the direction that's perpendicular to those would be pointing out radially from the wire. So a long antenna, such as in my grandmother's backyard, until she died a couple years ago, that long antenna is primarily going to send out radio waves horizontally. Is that good or bad? That's good. It's good because you don't really care about broadcasting your radio signal up to the International Space Station. Maybe you do. Most people don't. They care about broadcasting the radio station to the surrounding area, which is generally about the same elevation. And so a vertical antenna does a really good job of broadcasting out horizontally because the velocity has to be perpendicular to both the magnetic field and the electric field. So you have your television set. Now, you guys didn't grow up in my world. In my world, we had rabbit ears on our televisions. Okay. Those rabbit ears, you have these two things, and we play with the angle, we rotate it around, and it was like, I don't know how this works. I'm just going to adjust it until I get the station. We learned that, okay, we get channel 46 really well when we have it like this, and channel 8 really well when we have it like this, and we have to change the antenna for which station we're
It got so bad we bent the wires up shape.
Okay. Well, what's going on there? What you're doing there is the same idea as when you have an antenna on the rooftop of your car, which used to be really common with the CV ears. You don't see it as much anymore. You have those two wires, and one's supposed to be the ground plane, and one is detecting the signal. Now, if I have an electric field and I want to create a current in that wire, what orientation do I want between my wire and the electric field? Parallel. Parallel, because an electric field puts a force on the charge that's parallel to the electric field. I want the force of the charge to be parallel to the wire so it'll make the charge move in the wire, creating current. So I want my antenna to be oriented with the electric field. Based on what I just told you, that would seem to be vertical, right? Because you have a vertical antenna so that the signal goes out horizontally. And so if you have vertical receiving antenna, it should be receiving best. The problem is we don't have infinitely long antennae for broadcasting. And so depending on where you are, the geometry from where the station is, the angles can deviate a little. The ground plane, though, is going to work best, at least in theory, if it's perpendicular to the receiving antenna. So you would typically want those two to be at 90 degrees. On your car rooftop, that works out perfectly. You have the antenna pointing straight up, and then you have the ground plane of the rooftop that's horizontal. So this is called an electric dipole antenna because it will receive the electric fields and create a current that goes up and down in that. Now, let's take an example from lab yesterday. In lab yesterday, the part that we skipped, sadly, was the part about the resonance, observing the resonance behavior. The resonance behavior, if you tune the inductor and capacitor correctly, you'll have the total reactance is 0. Because remember, the inductive reactance was plus 9 degrees. The capacitive reactance was minus 9 degrees. So they're in opposite directions, and if you have the right frequency, they'll have the same magnitude for your L and C. So by adjusting the values of L and C, traditionally you just adjust the capacitor. It's easy to adjust capacitance. You can tune to a specific frequency. And what that's going to do is it's going to say, okay, I have this antenna, and I have lots of electromagnetic waves coming by. And some electromagnetic waves have frequency 1, some have frequency 2, and so I have currents that are oscillating due to all of these electric fields. But I only want one of them. And so you have that tuner that makes it so it's resonating at one frequency, and the other ones it's not. What should have happened, what would you have seen at resonance in your experiment? You would have seen a big jump in the voltage across the resistor, or in translation, a big jump in the current at resonance. And so having that resonating circuit, the inductor, capacitor in series, you adjust that capacitance and you can choose just one frequency to be selected out of all of the oscillations that are being picked up by the antenna. And so you can tune to just one station, even though that antenna is capable of tuning into a lot of stations. Now, that was an electric dipole antenna. Now we're going to have a magnetic dipole antenna. Magnetic fields. How would you detect a magnetic field? Carry around a piece of iron. I've got my compass. Well, what we do is we know that from Faraday's law of induction, change the magnetic flux through a loop will create a current. And so for a magnetic dipole antenna, you're going to make a loop. That loop may look like a circle. That's very common. Or it may look something like this. Oh, that's not it. I have a number of antennae that came like this. It might even look like this. But you have a loop. And then if you have a change in the magnetic flux, that is if the magnetic field going through the loop is changing, it'll induce a current. So if that's the case, if my magnetic field is oscillating like this, what orientation do I need to have my magnetic dipole antenna? Yeah, I need to have it like this so the magnetic flux is changing. So the orientation of that antenna is going to be a different orientation than you would have for the electric dipole antenna. And this responds if you have magnetic field going like this or going like this, and it's to the change because you had the induced EMF is equal to minus N change in magnetic flux. I already wrote the flux. Over change in time. So different orientation, that's measuring the magnetic fluctuations, whereas the rod is measuring the electric dipole, the electric field fluctuations. This is just a picture to show what I just showed on the previous page. If you have magnetic field and it's getting stronger, then magnetic field's that way, it's getting stronger, it's going to induce a current this way. Magnetic field's that direction getting weaker, it's going to induce a current the way that's shown. How do I know that? Lenzs law. Lenzs law says the direction of the current is the direction to oppose the change in flux. Go ahead, Claudia.
Can you repeat what you just said? You said magnetic field's getting stronger.
Okay.
Than you what?
So Lenzs law. That's Lenz's law. The induced current creates a magnetic field in the direction to oppose the change in the magnetic flux. So in this picture right here, the magnetic field is going away from you. So if the magnetic field is going away from you and getting stronger, then to oppose the magnetic flux increasing, you need to make a magnetic field that's opposing, so the magnetic field needs to come out. If the magnetic field is getting stronger, then the induced magnetic field is coming out, which means the current is going counterclockwise. On the other hand, if this magnetic field is getting weaker, then the induced current is going to try to add to the magnetic field to keep it from getting weaker. So it's going to go like this, and then the current's going clockwise as shown in the picture.
Okay, so just to clarify, if the magnetic field's getting stronger, it's gonna like counteract it. And then if it's getting weaker, then it's gonna try to amplify it so it'll like go with it.
So yeah, because it's trying to keep the magnetic flux the same.
Yeah, like balanced. Okay. So Lenz's law is about how the magnetic flux should be balanced.
Yeah, it's yes.
Okay.
Okay, that's the end of what I have prepared for today. That is like my epically short lecture. That is our chapter 24 coverage. And then we will start with optics on Friday.
Review for the exams on Monday.
Yeah, I think so. Well, a little and then go on. Yeah, class is over. Yeah, absolutely. Okay, let me.
You know, when we talk about instance, I cannot think about
So what more homework is they look like?
It will not have any calculations. It'll just be.
Oh, I
Yeah.
love that, because then you get one wrong, it's half the problem.
Sorry.
Wait, so the homework won't have calculations, it'll just be like random knowledge?
Well, not random. It's specific knowledge. Okay, which problem is?
We on number